for example, or x minus one,
Mhm.
wouldn't that be,
Then your base field, yeah, it's normal over itself. Right, any field's normal over itself.
but why would it be normal over the bigger field?
Well, what's the bigger field that you're talking about here? So let's start with Q, right? Q's your field. And you have something like x minus one. Well, Q is the splitting field, right? And so it's normal over itself. You haven't gone anywhere.
But wouldn't that any field extension would be normal?
No, because a field extension is not a splitting field of x minus one. X minus one, a splitting field for x minus one is the smallest field in which that splits, which is the base field itself. If you go up to a larger field, so go from, so hopefully I can help you out here, cure this a little bit. So if you start with Q, the splitting field. For x minus one over Q. Because it's already got a root in there, right? Or it's a linear polynomial of roots. So there's two things. You've got to specify the polynomial in the base field. Q is a splitting field, but cube root of two is not field for x minus one over Q because it's too big. The splitting field, remember what the splitting field over this field Q is it's Q adjoined with all the roots of this polynomial, which is Q. You've thrown some extra stuff in here and that's cheating. This isn't a splitting field. It is true that this polynomial splits here, but it splits in every field, but it's not the splitting field. But the splitting field is the small field. And then again, this is why you have to specify the base field. The small field over this from which this splits.
Okay, right. One
Yes.
more question. When we define separable, why do we want the roots to be different?
We're going to see that because let me refer you back actually to when we looked at when we were building up and proving the fundamental theory of Galois theory. At one point, and I believe I brought this up, that it was important that the roots are distinct, right? Because the automorphisms, in fact, I think I can refer you back to that. If you look back at
Totally inseparable extension is a good example of like why it's important because you can only have the trivial.
that's right, it can be Galois. So if you look back at right, look back toward the end of, I can't quite crack it down right now to give you a theorem number because this is talking about too much. But it was important that the roots are distinct because, yeah, Brad gave an example. I mean, if you have something that's totally inseparable, then the polynomial will be x minus root to the nth power, right? And the automorphisms don't do anything because they all have to fix that root, right? So there's, so that's why we care about separability because multiple roots give you problems. But we're going to give you some theorems in this that show you how you deal with this in the more general case. Okay, yes, Peter.
I have a question. I think that you told us that if we have an extension that for example, Q where you Q with adjoint U, and right, and F is the minimum polynomial of Q. If S was a row and has all its roots in Q, automatically the extension was Galois.
If you're over Q, and more generally, if you're over any characteristic zero field, If the extension is normal, then it's Galois. Because to be Galois, you have to be normal and separable. And any extension field that's algebraic in characteristic zero is a separable
Yeah,
extension.
but we can use the result, for example, for the homework.
Oh, what's the question then on the homework?
It was, oh, the second one, prove that if you have extension with degree exactly 2 and the characteristic isn't 2, then the extension is gone.
Yeah, well, what I would recommend you doing there is, basically, for that one, all you have to do is, look at the quadratic formula essentially. And so what in characteristic not equal to 2, which is the problem you're talking about, what you get is 2 distinct roots.
Yeah.
And that'll give you the automorphism that you need
Yeah.
to show that it's Galois.
And that's can you put in my next question? We can assure that we have that automorphism. I mean, the one that permutes these 2 roots is an automorphism of the whole field.
Oh, yeah. Because, well, what you do is you take your, whatever your base field is and you adjoin that root. The other root automatically has to be in there, right? And we have a theorem earlier that you can use that to induce an automorphism of that field. Right.
Okay.
Okay, other questions? Right, because your new field, when you join the root, is essentially that field adjoined with that root. You also have the other root in there, and it's easy to show that permuting the roots actually gives you an automorphism of fails. So, here's the last thing that I gave you, and we didn't prove it, so we will now. And this is kind of a really nifty lemma, and we're going to use it in the next theorem. If F is an extension of K, and characteristic of K is P bigger than 0, so prime characteristic. And F is algebraic over K, then U to the P to the N is separable. Okay. So, yeah. The natural number is using 0. So, what this means is you might be a mess, right? It might be purely inseparable. It might sort of be partially inseparable, if you will. It may not be separable. But what you can do is you can take this and jack it up by an appropriately high power of P, and it will become separable, right? This is actually kind of will be important. And of course, it's already separable, right? If U itself is what it could be, then just take N to be 0, and there you go. So proof. Here what we'll do is we'll go by well, essentially by induction of degree. So if degree of the minimal polynomial of U over K is 1, been done. Because after all, then what you have is U is in fact NK, and so it's minimal polynomial is X minus U, and of course that's already separable. Now suppose that the minimal polynomial that the minimal polynomial of a non-separable element of degree greater than 1, F, polynomial of a non-separable element. Of degree bigger than one. So let me ask you this. What do we know about this?
It has a common factor with that.
Well, but we have a result that's even stronger than that. This must be zero.
Right.
That's super convenient. So as we've observed before, F is a polynomial in x to the p, right? So that's the only way its formal derivative is identically zero. And so u to the p is algebraic. Degree less than the degree of u. So by induction, u to the p to the p to the n power is separable. So what we do is we just kind of reduce that. So this is kind of nice because what this says is, in a certain sense, if you have any element that's algebraic over K in characteristic P, you can sort of clean it, right? You can take it to a large enough P to the n power so that it's separable. And this will be useful in the next. So let me give you some equivalent conditions here. Suppose you have an extension field K. There. Let's suppose that F K equals 0, of course, and K is F. So that's algebraic. That's implicit in all these. Following the equivalent, number A, for 1, F is purely inseparable over K. F so it's a purely inseparable extension. 2, the irreducible polynomial of any u in F is of form x to the p to the n minus a in kx. If u is in F, then u to the p to the n is in k for some n, the natural number union 0. for the only elements of F separable over K are the elements of K and F is generated over F by a set of purely inseparable elements. Okay, so, let's talk about the proof of this a little bit. So suppose that F is purely inseparable. That means every element in F is purely inseparable over K, right? And what does that mean? That means its minimal polynomial is a linear polynomial to some power, right? So, come back to this. So what does this imply? This implies 4. Right? Because suppose you have an element of F, and it's separable over K. Well, if it's separable over K and F is purely inseparable, that means its minimal polynomial has to be in the form x minus u to some power. But if it's separable, that means that that power must be 1, which means that it's an element of K. Fine. Everybody okay with that? Okay. And this is key right here. So, what about this? What about the irreducible polynomial? I want to see a connection here. In a purely inseparable extension, why would this happen? That the irreducible polynomial of any u and f is of this form.
I use like a freshman stream kind of argument.
Well, right, but how do we know that the irreducible, so I know the irreducible polynomial. Let u be an f, right? I know it's irreducible polynomial. K power. That's what it means to live in an extension that is purely inseparable, right? Has to have that root. And of course, if u is already downstairs in K, then you can take K equals 1 and you're done. The big question though is, why must this be a prime power? What's that?
The derivative of the polynomial must be 0.
I'm sorry, what are the polynomials be zero, but,
Because the derivative of the polynomial must be 0.
okay. So notice. If u is separable, then K equals 1, and if K bigger than one, then U is not separable. And, and the derivative of that is 0. But really, all this means is that K I really need M to be 1, don't I? Huh. So how do I put the finishing touch on that?
M is not one, then we can look at the element like next to the A or something. Or,
Kind of separated out.
Okay.
Like we get X, C, or P.
Excited. So, well, suppose you have X minus U, let's say P to the A M. And let's actually assume here the GCD. P and M is 1. Right. So pull all of it out. So what does this mean?
U to the P to the A.
But right now that exists on A, that U to the P to the A belongs to K.
Okay. So this means that you, the minimal polynomial of U to the P to the A, uh, right, that the minimal polynomial of U to the P to the A is, so the minimal polynomial of U to the P to the A is divisor of X to the P to the A. Agree. Now, somebody explain then why M has to be 1.
Well, we're assuming extension is,
Right.
totally inseparable, right?
Mm-hmm.
So the fact that M is relatively prime to P means that, U to the P to the A is separable.
Okay.
The derivative of that, is non-zero, right?
So it's separable, so it must be in K. So this coefficient actually here is in K. So X minus U And of course, x, or I'm sorry, u is the root of this. Since this polynomial is in kx, then that's exactly what you need. Notice that this also gives the condition that I erased. That if u is in f, then u to the p to the n is in k, or so, you know, right? And so the rest of them connect up kind of like this. So what we're going to see actually is the fact that a purely inseparable extension actually has this very kind of nice, I like this right here. If you have an element of a purely inseparable extension, it's got a very nice form of its minimal polynomial. Let me give you kind of a corollary to this. Corollary, 849. If the characteristic of K prime, and F is finite dimensional and purely inseparable, so these are kind of two important things here. The finite, the finite degree extension is important, and F is purely inseparable over K. Then anybody want to take a guess what this is? Yeah, it's got to be some power of P. Okay, so how will we prove this? Um, Yeah, it is on how we would actually prove. I mean, it seems, given our experience here, I think it seems like, well, this has got to be what the answer is, but how do we actually show it?
I think we can inductively reduce to the case where we have a primitive extension.
Okay, okay. So let me start with this observation here. Let u be any element of F. Since u is algebraic over K, I know this for two reasons, sort of. One is it's purely inseparable, and just by definition, when you talk about purely inseparable extension, you're talking about something algebraic. But even stronger than that is the fact that I know that this is a finite degree extension. So since U is algebraic over K, and F is purely inseparable, okay, it must be the case, then minimal polynomial U over K is a form so the degree So what we're saying is the degree of any simple extension, any intermediate simple extension on PPN, right? So let's suppose so that's the first thing, and notice that, this is the form. So GCD. A1. Of course, let me point out that n could be 0 because we could have the trivial extension. We could have the F and K. I don't think there's anything in the statement my corollary that includes this. And again, we're in this wrestling match to show that A is not 0, right? Or I'm sorry, show that A is 1 is what we show. So how do we do this?
Well, one way we can do it is we can note that KU is also purely inseparable.
Mhm.
So we can just keep throwing on extensions, primitive extensions, because we until we get up there.
Yeah. If there's nothing that's an F that's not a K, then it certainly must be case it in as 0 equals 1, right? If not, there exists. So now what we have is we have degree here is P to the M. So the degree here must be P to the N minus M A. Correct? Now, we just keep doing this, right? This degree must be P to the M1. And what's left over here must be P to the N minus M plus M1. What's A or times? Oh, right. Yeah, minus M. Et cetera, et cetera. Because of course, these are all finite, and there's only finitely many steps. If we ever terminate, we get this situation here, or a similar situation, I'll say. And this extension must be A. But notice that this extension is purely inseparable here. after all, it's purely inseparable over K, so it has to be purely inseparable over the intermediate extension. So A is one. Right, because for it to be purely inseparable, if there's an element here, then there'd have to be another intermediate extension of degree at least P. Okay. Any questions on that? Okay, so here's another one of these ones that is going to be sort of part definition and part theorem. So theorem, theorem 8.4.10. Let F be an algebraic extension of K. As set of separable elements, that are separable. Okay. And P, the set of elements that are purely inseparable, okay? That are purely inseparable. Okay. So here's where the theorem kicks in. One, S is a separable extension of, okay. So this set of separable elements actually forms a field, and it's a separable extension of K. F is purely inseparable over S. So of course, F, we now, in part one, have established that S is actually a field. So F is a field extension of S. And F is actually purely inseparable over S. P is purely inseparable over K. And it's tempting to think that, well, okay, then F is separable over P. Well, let me do this first. Oh, I think we know this one. So you take the purely inseparable elements over K and the separable elements of K, their intersection is K. And here's the one that I was kind of hinting toward. It's tempting to think that F is separable over P, maybe not. Here's the condition. F is separable over P if and only if F equals SP. Of course, F contains SP, right? And if F is too big, if it's actually bigger than SP, then it's not separable. And finally, the sixth, F is normal over, if F is normal over K. then S is Galois over K. Of course, F can't be Galois over K unless it's actually separable over K. And so S is sort of the separable analog of that. It's all separable elements. So if F is normal, then S is Galois over K. F is always Galois over P. Again, that's, not a total non sequitur. We need F as normal over K for the F to be Galois over P. I'll make that better. And the automorphisms of S suffix K, same thing as the automorphisms of F suffix P. So that is to say, Galois group of S over K is isomorphic Galois group of F over P. Which is actually the automorphisms K over F, because remember what happens with purely inseparable elements is the automorphisms only take that single root to themselves. So here's kind of what, I'm trying to draw a diagram of this, if you will. So you could take the separable elements, the nice ones, over K. Here are the ones that are purely inseparable. And these are all picked out of, these are all contained here. And, well, actually, let me go here. Here you can make the field SP, which is the smallest subfield of that. It contains both P and S. Now, what is true is this is a separable extension. This is a this is a separable extension.
Shouldn't that be,
Oh,
SP?
right, got the thing turned around, this is separable. And this one right here is, well, this is purely inseparable. In fact, both of these are. And this one, of course, is purely inseparable. So if these two are the same, then this is actually separable as well. So basically what this theorem tells you is, given this algebraic extension here, you can sort of dissect this. You've got your separable piece, and then you've got your purely inseparable piece. And these two intermediate fields kind of govern what goes on in a certain sense. So, this proposition, if it's not homework. Separability is transitive. So if F is separable over E, and E is separable. Okay. Then F is separable. I'm gonna leave this, and the next one is an exercise. I know the next one for sure is, in the homework. Corollary. Well. Suppose that you have a characteristic P field, and let it be an algebraic extension of said field, then U is separable over K. If and only if so this is kind of a nifty way to sometimes tell if you've got a separable element or not. If you have an algebraic element U over K and characteristic P, but look at these two fields. If you get equality, right, then U is separable. Of course, you always get this containment here, right? So the trick, of course, is the other one, and that gives separability. This is a fun problem, and it's in your homework, so think about this. Okay, so let's kind of look at our diagram again here, and I'm gonna kind of file a definition here. Okay, this is a definition. Let's suppose that F is algebraic over K, F is the largest subfield that is separable. Take S, E as in, theorem 8410. So I'm going to use this notation here. The degree S over K is called the separable degree. Separable degree of F over K, and is written sometimes as so when I have FKS, that just means every element in F that's separable over K, that's a field, and figure out what its degree of its extension is. F over S is actually called the separable, is called the inseparable degree. and we sometimes write this way. F, K. So we'll use those definitions next time. Turns out separable degree and inseparable degree behave like you would hope they would. Any questions? Questions? All right, well, we will get to this next time. You all have a good one and we'll see you on Wednesday.